Hello everyone and welcome. In this video we're going to introduce search algorithms. Before we dive into search algorithms, we'd have to first distinguish between two separate key concepts. The first concept is state space, while the second is search trees. Okay, so what is a state space exactly? Let's say we have the cities of Romania plotted in front of us, where each city is represented by a dot, and each city is connected to its neighboring city through a line. Okay, so a dot right here in the state space represents a state, and the line represents an action. So an action is basically what you do to transform between one state to another. And on each action or on each line, there is a number plotted on that action. This number 2 represents the cost of the action. In this case, the action we have is traveling between one state to the other. And this number could be the distance required to travel to arrive from one city to the neighboring city. So, next question is, how do computers tackle this problem? I mean, how computers search the state space? First of all, the computer takes a starting point or a node and expands that node. What does that mean to expand the node? Okay, so in a search tree, you have a parent node, and the parent node, there are branches that do emerge from that node. The branches here do reach a certain node. I mean, like each branch have a certain node at the end of it, and that node could be expanded to more and more nodes. So we can see in this case, the nodes that have been expanded are the neighboring cities of the starting point, in which case is Arad. So the next thing is what the algorithm is going to do is that it is going to expand the next node. So some algorithms do expand nodes in a certain order, and some algorithms do make some informed decisions in order to decide which node it is going to expand next. So let's say I want to go from Arad to Bucharest, okay? So let's say we just want to expand Sibiu next, this middle node right here. And we can see that Sibiu expanded into 4 other different nodes. And one thing to notice is one of those nodes is Arad, which is its own parent city. Which does make sense because each city is connected to its parent as much as its parent is connected to it. The set of expanded nodes in this case is called frontier. And each node in the frontier is called a child node. One awesome property about search trees is that each node has multiple children nodes, but each child node has only one parent node. This concept allows us to use something called backtracking. So let's continue our search algorithm, or let's continue our path to Bucharest. Let's say we decided to go to Făgăraș, next state, and then Bucharest. So we can see that the tree has expanded to 4 different levels right here. And when we have reached Bucharest, we want to trace back, or we want to know, okay, so we have found Bucharest. How do we get from Arad to Bucharest now? There is a certain path that we should take to get to this state. So what you're going to do is going to use the backtracking method, which uses the awesome feature of trees that each node has one parent node, and go trace to the parent node of each node until you reach the root node of the tree. One last thing to notice here that in this tree, some nodes that have been expanded into nodes that you have already visited. Like for example, Sibiu here expanded to a couple of nodes, and one of these nodes turns to be Arad, its own parent node, and also a node that have been already visited. In our search algorithm, when we design it, we don't want to visit a search node or visit a node that we have already been through, because that would be inefficient and time consuming. And in some cases, it can lead to uh, being stuck in a loop where you are visiting the same cities over and over again. Next up, we'll have to discuss the evaluation of search algorithms. So, to evaluate a search algorithm and say if a search algorithm do perform better than another, we'd have to lay out some performance metrics. So, first performance metric is completeness. When to say an algorithm is a complete algorithm? An algorithm is considered complete when it is guaranteed to find a solution. So, if an algorithm is basically guaranteed to cover up the whole search tree, that means that it is complete. Next up is cost optimality. The algorithm is considered a cost optimum algorithm when it hunts for the path with the lowest cost. So this could be extremely useful when you are interested in finding, for example, the path between two cities that have the lowest cost, meaning like the path with the lowest distance to go to another city. Next up is time complexity. So time complexity, it's basically the amount of time that the algorithm should take to solve a certain problem. And it's mostly associated with the number of states the algorithm has to cover. Next up is space complexity. An algorithm is considered complex in terms of space when it needs too much memory. Any algorithm basically have to store some data about the search tree, and some algorithms do need to store more data about the search tree than the others, which make them more space complex. And this is a very important metric because a computer memory can only store so much data until you run out of memory, and this would cause a serious issue. Next up, let's discuss some measurements for problem difficulty. So, first of all, we have two types of problem definitions. Firstly, is explicitly defined problems, which are the problems that can be laid out on a graph, similar to the state space of the cities of Romania. So, explicitly defined problems are problems that are defined with vertices and edges, which are states and the actions that you need to take to transform from a state to another. Secondly, is implicitly defined problems. An implicitly defined problem is when you are discovering an ambiguous environment where you don't know what the next state is gonna be unless you perform a certain action. Next up, let's talk about some variables that we're going to use to identify complexity. First is lower letter D. So the lower letter D basically represents the depth at which the solution exists. And then we have M, which represents the deepest level that you can reach in a search tree. And then B is just a branching factor, which represents the number of branches you can expand from a node. So that will be it for the introduction, and see you in the next video.